Well, good morning, chemistry kids. I hope you guys had a great weekend and enjoyed maybe some Easter fun with the family. We had a Zoom meeting, yeah, I know, with our extended family, so that was kind of fun to see everybody, kids home from college and just my nephews, my nieces, bunch of uncles, all that good stuff. So hopefully you guys were able to do that. And maybe this weekend, because you're not too old to do this, you decorated some eggs. Here's a few of the eggs that we decorated. That was one that I started messing around with. And, we kind of got, I like blue, so I made some different colored eggs like that. Eventually that led to this guy here. I'll let you guess how I made that one. All right, you guys think about that. We got a couple other interesting eggs as well. We had, just your kind of general colored egg and things like that. But I'm curious if you ever saw these egg sleeves. They're basically like little pieces of plastic that you wrap around the egg, okay? And then you dip it in some boiling water really quick and it shrinks within like 2 or 3 seconds. Kind of fun. A lot of chemistry involved there. When you think about it, it's weird because usually when things get hotter, they expand. They don't contract. However, if you think about like a milk jug, if you took a piece of the plastic that makes up a milk jug and you started to heat it up, don't burn it, but you start heating it up. Let's say you got one in your recycling bin. Take a second, maybe hold it over some heat and see what happens to the color and the size of that plastic. We can talk more about why those changes happen later. Anyway, I thought this one was cool. It was dyed blue and then it got dipped into a red cup of dye that didn't fully dissolve. So there were still like chunks and stuff in it. And this part here never got dyed all the way blue because the blue dye wasn't really full in the cup. So it left the egg white. And then when we put it in this pink dye, it looks like an egg within the egg. At least that's what Joshua was telling me. I thought that was neat. I thought it looked pretty cool. All right. You get the idea. Pretty cool stuff. Anyhow, so yeah, and then we dyed this one. Oh, this was really a beautiful, no, that one's from China. Okay, we got a few of those. So maybe you did a little Easter egg hunt. You went around, found some of those. We had some candy placed in our eggs that we had outside for the kids. So that was fun getting out there. Well, I wanted to walk you through the problem set on colligative properties, and that's this one right here. So if you want to grab that, all right, we can take a second, go through that. I know I showed you the first 2 problems, so you already had these done, but you might have wondered how to do some of the, actually how to do some of the other problems. And it's always nice to walk through a problem together. So with that being said, if you just want a quick snapshot of, or you want to pause the video and just see for yourself, boom, there you go. You can do that. Otherwise, I'm going to walk you through all of the problems together, or at least all the ones on the first side. So one of the first things I do when I see a freezing point depression problem, or when I see a boiling point elevation problem, is I look to see which of the equations I need to use first. So this one obviously says we've got a change in freezing point. So I know I'm going to use delta TF. And if you remembered in the very beginning, when I gave you this problem set, there were 2 equations that we need to focus on. We got delta TF and delta TB. One is the change in boiling point. The other is the change in freezing point. So if you look at this guy here, he's got a different constant than this one here. And that's dependent upon a few other things that we're going to talk about later as I introduce you how to make your own ice cream at home. Because making your own ice cream at home usually involves salt and putting salt in ice so that you can lower the freezing point of the water. It's pretty cool stuff for sure. So let's take a look at this problem. All right, what's the change in freezing point? So right away I know I'm dealing with the delta TF, and so you can see that equation written here. And we're talking about 35 grams of antifreeze, which is ethylene glycol. That's the main ingredient. And here's the equation for the ethylene glycol. Now, this is dissolved in 125 grams of water. And you might be wondering, why are we talking about grams of water? Why aren't we using milliliters or some sort of volume unit? And that all comes down to the fact that we have this new quantity called molality, which is just like molarity, except instead of moles per liter of water, it's moles per kilogram of water. Whereas if you know, a kilogram of water is going to be equal to a liter of water in regards to what we learned earlier in the year. 1 gram of water, which is a mass unit, equals 1 milliliter of water, which is the volume unit, because water's density is 1 gram per milliliter. And so, of course, the same is true. A kilogram of water is equal to a liter of water. All right? So, because again, the water's density is 1 gram per milliliter. So let's take a look at this. We've got 35 grams of ethylene glycol. Now, I'm going to need to find molality in this case. I don't have it. I don't have my lowercase m molality. And again, that's how many moles we have in a kilogram of water. I don't have that. I'm wondering what that is. But I am given the mass unit, or I'm sorry, I am given the mass, how much antifreeze I have in grams. And so I can actually get the moles of ethylene glycol by just dividing by the molar mass of ethylene glycol. All right, so you can see I found that I got 0.56 moles of ethylene glycol if I had 35 grams of it. And of course, I know how much water I have. If you look in the problem, it says I got 125 grams of water. But we have to change that grams to kilograms. And so I just moved my decimal over to the left 3 times. And now I can divide moles by kilograms. And I get a molality. Now, if I'm using sig figs, which I am here, I got 2 sig figs for 35 grams. My molality, my M, is 4.5. All right, and that's moles per kilogram. That's the molality of my solution right now. So I can take this and I can plug it into the delta TF equation. I'm going to use 1.86 because that's what we use. That's the constant we use when we're dealing with this substance. And I am just going to multiply my 4.5, my molality, times that 1.86. And you're going to see that I get 8.4 degrees Celsius. Now remember, this is not the new freezing point. This water is not going to freeze at 8.4 degrees Celsius. This is the change. That's why there's a delta symbol right there. This is the change in freezing point. So if I was to ask you a question and I said, hey, what's the new freezing point of the water that you added 35 grams of ethylene glycol, antifreeze, to? If you had 125 grams of water or 125 milliliters of water, what would the new freezing point be? If I asked you that question, you would tell me that the new freezing point is, think about it, if I changed the freezing point by 8.4 degrees Celsius, and this is called freezing point depression, well, what's the freezing point of water? The freezing point of water in Celsius is 0 degrees Celsius. So if I depressed the freezing point by 8.4 degrees, then my new freezing point would be, yep, you got it, negative 8.4 degrees Celsius. Great. All right, so that's how you would do that problem. All right, let's take a look at the next one. This one says, how many grams of ethyl alcohol must be dissolved in 300 grams of water and in order to change the freezing point by 2 degrees Celsius? Now, I think this is cool because now you've got in your mind a certain temperature you want to be at, right? I want to change the freezing point of water by 2 degrees Celsius or 5 degrees, or maybe I want to lower the temperature. I don't want water freezing until I get to negative 15 degrees Celsius. So it's kind of neat that you have the ability to do that. And different substances that you would use as a solute in water, different substances that you would dissolve in water, will be different amounts. You would add them in different amounts depending on what the freezing point depression is that you're trying to achieve. So take a look at this one. How many grams of ethyl alcohol, right? Are we going to need? We got 300 grams of water, 300 milliliters of water, and we want to change the freezing point by, well, it says negative 2 degrees Celsius. So of course that means that the delta TF is a positive 2.0 degrees Celsius. We want to change it by 2 degrees Celsius. It's already assumed that you're going to go down, right? Again, it's freezing point depression. You're going down, all right? So I'm going to use this delta TF equation right here. I'm going to use this constant. And I'm just going to go ahead and I'm going to write the equation out. As you can see, my delta TF, my change is 2 degrees Celsius. My constant's 1.86. But the thing I don't know is I don't know my molality. So, of course, I can get molality by itself just by dividing both sides by 1.86. Okay? And when I do that, I get my new molality right here. Now, be really careful because this is my new molality, and molality is how many moles you have per 1 kilogram of water. Well, do I have a kilogram of water? No, I don't have a kilogram of water. Let me try to make that bigger for you. All right, it's kind of weird with my, I got eggs rolling off the table. That's awesome. All right, here we go. All right, so I don't have a kilogram of water. All right, how much water do I have? Well, I got this much water right there. I got 300 grams of water. Okay, so I've got to make that adjustment. Mathematically, I'm going to make that adjustment just by multiplying. See how they cancel out? Kilograms of water, kilograms of water. I just multiplied by how much water I actually have. But don't forget to change it to kilograms. All right, so I go ahead and I do that. Oh, wow, now this is showing me that I've got 0.33 moles of the solute, of what's dissolved in the water. In this case, it's the ethyl alcohol. All right, cool. So now I know my moles, and I can take my moles and just multiply by the molar mass. So I take my moles, I multiply by the molar mass of ethyl alcohol. That's what my EA stands for there. I didn't write out the chemical formula. And I'm able to get from moles to grams, which you guys are experts at. You've been doing that for a while. So the answer here is 15 grams. All right, it would take 15 grams to change the freezing point of 300 grams of water by 2 degrees Celsius. We'd lower it 2 degrees Celsius. All right, let's take a look at the last one on this page, and this one's a little bit different. You didn't have an example for this, and it's something we would do actually in our in a lab. And I'll talk more about that also. But let's take a look at this problem together. It says, it's found experimentally that 1.8 grams of sulfur dissolved in 100 grams of water or 100 milliliters of water. You'd have to be careful because in college, you might get a problem that actually says you've got 100 milliliters of water. They might be, a little sneaky there. Not that they're trying to be, but we should know at this point that 100 milliliters of water is 100 grams. So don't be hunting around for that gram unit when that's something you would be able to figure out on your own. So let's take a look here. We got 100 grams of water. It decreases the freezing point by only 0.48 degrees Celsius. That's not a whole lot. What's the molecular weight of the sulfur compound? Whoa, all right, molecular weight. Well, if you guys remember, molecular weight is basically the molar mass, okay? So, just like the molar mass of an H2O molecule is 18 AMU, or molar mass, it would be 18 grams per mole. If I wanted a mole of water, I'd have 18 grams per mole. So they're trying to say, hey, what's the molecular weight of this sulfur compound? Now you might think, why do we need to know that? Well, actually in forensic science, forensic chemistry even, knowing the molecular weights of certain things like gases helps you identify what they are. You might not know what a substance is, but if you can figure out its molecular weight, you can come pretty close to narrowing down what it is that you're working with. And that's pretty cool too. We have a lab that we do where you actually measure and find the molecular weight of a gas, and you're able to determine what it is. So let's take a look at this one, all right? I, again, am going to use delta TF equation, because we're talking about freezing point. And if you look here, remember, I've got to get grams per mole. I got to get my molecular weight. I've got to get grams per mole. What do I have already? Well, I've got 1.8 grams of sulfur. Well, okay, cool. What can I do with that? Well, that's the grams part of my molecular weight. I've got that. But I don't have the moles. Well, how can I get moles? Well, I can get moles by finding molality. So I'm going to take everything again. I'm going to isolate M. I'm going to get M by itself. And when I do that, I find that I have 0.26 moles of this sulfur solute in a kilogram of water. Remember, this is in a kilogram of water. When you solve for M, you are finding what's in 1 kilogram, 1 liter of water. All right, you basically found that you have a 0.26 molal solution. But I don't have a kilogram of water. I've got 100 grams of water. So I am going to multiply by 0.1, all right, to get how many actual moles I have. And in this case, I've got 0.26 moles, all right, total. Well, cool. I now know my moles. I've got grams, I've got moles. I just figured it out, 0.26. And if I just take the two, I can go and divide my 1.8 grams that I found by the 0.0. Oh, I wrote 0.026. Well, that ain't right. I got to figure out what that is here real quick. All right. Well, I didn't have a calculator because I was using my phone as a calculator, and obviously I am recording with my phone. So this here is 0.026. I made a mistake when I wrote that down. And I've got it correct here, but I just missed that 0. So when I divide 1.8 by 0.026, bam, I get 69.2 grams per mole. That is the molar mass of my sulfur compound. All right, so hopefully that was helpful for you, walking you through these 3 problems. The problems on the back, which you already have the answers to from my other post, are done exactly the same way, especially this molecular weight one, which might be a little bit more confusing. So give those a try on the back. The other thing that we're going to be doing, you're probably wondering, well, what's a little bit new in regards to material that we're going to do this week? Well, I'd like you to actually try using some of these principles here. I want you to try, I want to turn on my flash. I'll get that later. I want you to try, try making some ice cream. This is one of the labs that we do that's just super fun. And if you've never made ice cream before, some people get really, they've got the ice cream making machine at home. You don't really even need that to still make ice cream. But I'm going to walk you through how to make some ice cream at home. And really all you need is some whole milk at the least. Now, you can use 2% in some of that, but there's more water in it, so it's not as creamy. And a baggie and some sugar and some flavoring, a little bit of salt, of course, for lowering the freezing point, and I'll talk more about that later. But I'm going to post that for you, and even post a video of what it looks like to make ice cream at home the simple way, just using some baggies. You're going to want some gloves, all right? But this is the lab that we would follow to make our ice cream. And you'll notice here that you do have to, if you're wondering, like, well, when are we going to use this in the lab? You do have to find the molality of the salt solution that you make when you go to make your ice cream. What this means is that you guys are going to be throwing some salt down on some ice to get that water really, really cold. You throw the salt on the ice and it melts and turns into water, obviously. But as you add more ice to the water, it cools the water down more and more and more. And that makes the water, get down to like -6, -10 even. I've seen in our class, -12. It gets really, really cold. And it basically takes that milk and sugar mixture that you have, and it turns it creamy. It gets it nice and kind of hard. So you would have to take that ice cream and you massage it. I know it sounds kind of crazy, but you want to wear some gloves and get it to, and it takes about 5 to 10 minutes, but and it usually comes out pretty well. So I'm going to show you how we would go about doing that. But my point here is that in the end, you would actually take a sample of your salt water, not the ice. So you'd have a bag full of icy, salty water, and you would pour some out into a beaker, and you would measure out how many milliliters you had in this beaker, right? And let's say you had about this much just in there, I don't know, let's just call it about 50 milliliters, all right, of water, and this is a salty water. And then you'd come back in a day or so, we would actually evaporate this, and you would see that you would be left with just these chunks of salt, all right? And we'll just call it NaCl, all right? We'll say that it was table salt. And you would be able to measure how many grams, here's the application, how many grams of salt you had in so much water, right? So if you look here, we actually have moles. We could get to moles, and this here would get us to grams and then kilograms. So we would have moles per kilogram. We would have molality. And we could figure out, what should the change in freezing point, what should the freezing point depression be for my solution that I made in class, and on my thermometer, right? This is supposed to be a thermometer, but on my thermometer, what did I actually see? Did I get like negative 10 degrees Celsius? So you would just compare your theoretical calculation to your actual experimental calculation and see how close you're able to get. It's pretty cool stuff. So anyway, with that said, let me put this online for you, and I hope you guys have a great day. Again, I wish I could see you. I will post on Google Classroom when we're gonna meet next, but I hope this walkthrough of the problem set is helpful. And again, stay safe, have a great day, get outside, breathe some fresh air, and we'll look forward to talking to you soon. All right, take care.